Hello everyone, welcome back to my channel. In this video, we're going to discuss about a very important concept of structure of atom chapter, and the concept is about the de Broglie concept, right? Now, directly going into the definition of this theory, or we can say the concept, let's try to relate it and understand it properly. Now, previously we have understand the Planck's quantum theory, right? And what does it say? The Planck was a scientist who said that light possesses the particle nature also, even though it has wave nature. We know the wave nature of light was explained by James Maxwell. So there was a scientist called James Maxwell. So James Maxwell was a scientist who described that light has a wave nature. And after that Planck came and he said that light possesses the particle nature also. The light has particle nature also, and the particle nature of light is expressed in the terms of photons. And we know what are the photons. Photons are in a way the energy carriers of radiations, right? They are the energy carriers in the case of radiations. Now what is the de Broglie said? De Broglie just reversed this concept, because see, the Planck said that light has wave nature as well as particle nature, right? So de Broglie said that if we talk about any matter, now we know the matter has mass, so any matter will have the particle nature. Any matter will have particle nature. So de Broglie said that any matter which has particle nature can also have the wave nature. So in a way, he discussed the dual nature of a matter. Dual nature of matter. This is what de Broglie said, right? It is in a way reverse of Planck's theory. Planck said that light which already has wave nature can also have particle nature, and de Broglie said that any matter which has particle nature can also possess the wave nature. In a way, he talked about the duality of matter. But the important thing is, how did he relate these two concepts of particle and wave nature of a matter? So to do this thing, let's derive the de Broglie equation. Now let's derive the de Broglie equation with respect to the radiations only. Now we know in the radiations, or let's be specific, in the case of light radiation, it is the photons that are the energy carrier. Photons are the particles, right? This is what we assume, that photons are the packets of energy which are the carrier of energy for the radiations. Now here, if I say energy of a radiation is equal to what? Energy of radiation is E is equal to h nu. This is the first equation we know. Now if we say the radiations contain the packets of energy, that is the discrete packets of energy, which are photons, and if the photons have particle nature, then they will have energy E is equal to mc square, right? This is the energy of photon in the terms of particle nature. So this first equation describes the wave nature. It utilizes the wave nature. Second equation utilizes the particle nature. Now why it utilizes the particle nature? Because here we are using the mass, and definitely any particle will have the mass. And also we know that photons travel with the velocity of light, so that is why we are using the c. Here c is what? C is the speed of light. C is speed of light. Since both energies are related to the single entity, that is the radiation, so what do? We equate first equation with second. So on equating first equation with second, what do we get? We get h nu is equal to mc square. Since nu is what? Frequency, which is also equal to c by lambda, so hc by lambda is equal to mc square. Now from here, simply the c will cut off, so what do we get? The remaining thing is h by lambda is equal to mc, and which finally comes out to be lambda is equal to h upon m into c. This is the final equation which we obtained. Important thing is, we are still deriving this equation by using the radiations, right? In the radiation we are utilizing the wave nature and particle nature. Now lambda is equal to h upon m into c, right? In this equation, this lambda is equal to h upon m into c. In this equation, we are having both wave nature as well as the particle nature which are related to each other. So if the radiation has a wave nature, it will have lambda wavelength, right? And if this radiation has particle nature also, so it will have the mass m, basically the photons, right? So both wave nature and particle nature are related here. One more thing is there. We know that momentum p is basically what? It is mass into velocity v. And since here we are talking about the photons, and photons generally have speed of light, so their velocity v is what? Their velocity is written as c. So this equation also turns out to be lambda is equal to h upon p, where p is momentum. This is the final equation which we have. Lambda is equal to h upon p, and here lambda is de Broglie wavelength. This lambda is called de Broglie wavelength. Now important thing is here that de Broglie utilized the radiations concept to derive this equation, but finally he generalized this equation. So upon generalization he said that this equation lambda is equal to h upon p can be used, this equation can be used, it can be used for any subatomic, or we can say microscopic particle. This equation can be used for any subatomic or microscopic particles. So for microscopic particles, this equation is fairly, what do we say, applicable. We can easily apply this equation, right? So lambda is equal to h upon p is important equation. So if we talk about any other matter, for any general matter, general particle, now this general particle can be what? This general particle, it can be either electron, it can be proton, it can be alpha particle, right? It can be anything, either electron or proton or alpha particle. We can say that lambda is equal to h upon m into v. Here v is the simple velocity. Here v is not the speed of light, it is the simple speed of these particles, right? Because we know photons move with the speed of light, not the electrons, protons and alpha particle. So here lambda is equal to h upon v. This is the general equation, or we can say h upon p, right? One more equation we can derive easily from here is that, since we know that kinetic energy is equal to what? Kinetic energy is equal to half mv square, right? And definitely these particles are what? These electron, proton and helium which we have described here, these particles have mass, and if they move they will have some velocity also. Now since they have mass and they have velocity, they will definitely have kinetic energy. So the formula is what? Half mv square. Now what I can do is that I can derive a new equation. If I just multiply and divide this equation with mass, I obtain this thing. Here mv is what? Mv is momentum. So this equation is what? This equation is mv square upon 2m, which comes out to be p square by 2m. So that means kinetic energy is equal to, this thing we should remember, that kinetic energy can be derived from momentum by using this equation. Kinetic energy is equal to p square by 2m, right? Now p is what? I can write p equal to kinetic energy into 2 into mass and square root. This is how I can write the momentum, and we can use directly this equation of momentum in the de Broglie equation. So basically the de Broglie wavelength will be equal to lambda is equal to h upon p, which is equal to h upon 2 into m into kinetic energy, and with the overall of square root. So this is another de Broglie equation which we can use. So this is another variation of de Broglie equation. So far we have gone through two equations. One equation is lambda is equal to h upon p. Second equation is lambda is equal to h upon square root of 2m kinetic energy. These are the two important equations which we have derived from Debroglie. Third important equation we can also use. Third important equation is there. Now let's say we have a tube like this, just like we have used in the cathode ray experiment, right? Here there are two electrodes, and these electrodes are connected like this through a battery system, and it will provide what? It will provide us the potential difference V. Let's say any charge Q is there, which is placed here. Now the moment we will switch on the battery, what will happen? Now initially the charge Q is placed in between these plates, or we can say electrodes. Let's say here we have the plus charge and here we have the negative charge, right? Now we have no idea about the nature of Q charge. This Q charge can be positive or it can be negative, depending upon whether it is electron or proton or helium. So the moment you will switch on the battery, what will happen? This Q charge will gain some energy and it will start moving. But the important thing is, the moment initially the charge is at rest. Let's say initially we are assuming that initially the charge Q is at rest. We will assume this thing, right? Initially this charge Q is at rest. So if it is at rest initially and you switch on the battery by supplying the potential difference V, what will happen? This charge will gain energy. It will gain the electrical energy. You are basically supplying the electrical energy, which is equal to charge into potential difference V. This is the electrical energy you apply, right? Or we can say the moment we apply the potential difference V, it starts accelerating, it starts moving, and it gains the kinetic energy. Now the point is, from where this kinetic energy came? It is because of the motion. But to move the charge, we have to supply the energy. And what is that energy? That energy is electrical energy. So basically what has happened, that this electrical energy which we had supplied has converted into kinetic energy of charge, which is equal to half mv square, right? So basically in this way, this is potential difference V. Okay, so don't get confused, this is potential difference V. So this is another equation which we have obtained, that kinetic energy is equal to charge into potential difference V. So if I reuse the equation lambda is equal to h upon p, another equation which we have obtained is lambda is equal to h upon p, which is equal to h upon square root of 2m kinetic energy, which is again equal to h upon square root of 2m, and what is kinetic energy? Charge into potential difference V. So these are the three variations of Debroglie equation which we have obtained. So Debroglie wavelength can be obtained by using any of these equations depending upon the data which is given in the question, right? So three equations we have obtained: lambda is equal to h upon p, lambda is equal to h upon 2m ke, and lambda is equal to h upon 2m q into v. I will again repeat the last formula, that if we take any charge q, because we are talking about the particle, right? The de Broglie concept is utilizing the particle nature of matter and then explaining the wave nature. So if any particle q is there, or we can say any particle is there which has charge q, and when it starts moving in the presence of potential difference V, the electrical energy supplied is QV, right? And because of law of conservation of energy, this electrical energy converts into the kinetic energy of particle when it moves. So that's why kinetic energy is equal to electrical energy Q into V. Here V is what? Potential difference, right? I will write it there. V is what? Here V is potential difference applied. I hope you know the potential difference. We have learned this potential difference V in 10th class also, right? In physics. So these are the three important concepts of de Broglie equation. So I hope you understand it properly. Just go through it again and learn it properly. Now, what is the important application of de Broglie concept? There are three important applications. Two applications we will go through the questions, right? We'll understand how we can apply these equations to solve the problems, and third one we will apply to understand its significance. Now let's go through it. Now the question says, a question is there that an electron, proton and alpha particle are given to us and they are having the kinetic energy 16E, 4E and E. What is the qualitative order of their de Broglie wavelength? So the question is asking what is the order of their de Broglie wavelength. Now which formula is to be applied here is totally dependent upon what values are given to us, right? What data is given to us. In this question you are given an electron, a proton and an alpha particle, that is He2+, right? These are given to us. Electron has the kinetic energy of 16E, proton has the kinetic energy of 4E and alpha particle has the kinetic energy of E. So since kinetic energies are given to us, we will definitely use the second formula, this one. This formula we will use. Now this formula requires two things. One, the mass, because H is constant, right? H is Planck's constant, so it is not required right now. M is the mass of the particle and K is the kinetic energy of particle. The kinetic energies are given to us and we need to know the mass. Now we know the mass of proton is how much? Mass of proton is 1 AMU, right? And mass of helium particles is how much? 4 AMU. Helium particles has the mass of 4 AMU, right? This we know. So by using these mass, what we can say? We will directly apply the equation, right? So lambda is equal to the mass of electron is how much? It is 9.1 into 10 raised to power minus 31 kg, right? This we know. What about proton? Mass of proton is 1 AMU and mass of helium particle is how much? It is 4 AMU, right? This thing we know. Another thing which we know is that mass of electron is very less as compared to mass of proton, right? If you write, we will say that mass of electron is 1853 times mass of proton, right? It is nearly like this. So you see the mass is very less. So what do? We will compare their wavelengths, right? We will take the ratio of their wavelengths. So lambda of electron is to lambda of proton is to lambda of alpha particle, like this. Now lambda of electron is what? Now in this formula H is constant, 2 is constant, right? So definitely I will do one thing. H upon 2 ME kinetic energy. ME means mass of electron into kinetic energy of electron. It is 16E. It is 16E, right? Square root is to lambda of proton. So H upon 2 mass of proton into 4E, again square root, is to H upon 2 mass of alpha particle He2+ and kinetic energy, which is E, again square root. So now if you see, I can easily cut lambda and lambda and I can easily square them also. Upon squaring and cutting, 2 is also gone and E is also gone. Square root of 16 is what? It is 4E. So this is 1 upon 4 square root of mass of electron is 2. This is 4, square root of 4 is 2. So 1 upon 2 square root of mass of proton, and this is how much? Is 2. 1 upon mass of helium, right? Mass of alpha particle, I can say. This is mass of alpha particle. Now if you look at here, now all these lambdas are what? All these ratio of lambdas are inversely proportional to their mass as well as some integer. Now if you look at here, the mass of electron is least. I have told you that mass of electron is very less. If I compare their mass in a way, mass of electron is very less as compared to mass of proton and very less as compared to mass of alpha particle. This is the order of their masses. So if this is the order of their masses, what will be the order of their lambdas? So lambda of electron will be highest, I will say. Then it will be, see, mass of alpha particle is what? 1 AMU, है ना? This we know. Mass of alpha particle is 1 AMU. So again, just a second, we can say this thing that we can further rewrite this equation. 1 upon 4 square root ME is 2. What is the mass of proton? 1 AMU. So it will be 1 upon 2 square root of 1 is 1 is 2. 1 upon mass of alpha particles. It is how much? Square root of, right? This is square root. So it will be square root of 4. Again this will what? This will be 1 by 2. It will be 1 by 2. So now you can easily see that here the ratio of lambda p and lambda He2 plus is same. The ratio of de Broglie wavelength of alpha particle and proton is same. That means alpha particle and de Broglie both have same wavelengths. So which option is there? Two options are there. It is either option A or option D. Right? Now one of these options is correct. But we also know that mass of electron is very less as compared to mass of proton. So definitely lambda of E is highest. So which option is supporting this thing? Option A. So therefore option A is correct. Right? So this is how we solve this problem. Similarly, in the next problem it is asking that what possibly can be the ratio of our de Broglie wavelength for two electrons having same initial energy and they are accelerated through 50 volt and 200 volt. Now the question is saying that there are two electrons. Let's say this is electron 1 and this is electron 2. This electron is accelerated through 50 volt. That means here the potential difference V is 50 volt, and here in this case the potential difference is 200 volt, right? So we know both are electrons, they will have same charge, and since they are accelerated through different potential differences, they will have different kinetic energy. Just now we have just understood this thing, that kinetic energy is equal to charge into potential difference, right? We have utilized this formula. So what do? We apply it here. In this case kinetic energy is how much? It will be E into 50. 50 is the potential difference and E is the charge of electron. This is Ke1. What is Ke2? Second kinetic energy is again charge into potential difference. So how much is the charge? Charge is E into potential difference is 200. So this is Ke2. Now we'll do what? We'll take the ratio of their lambdas. So lambda 1 upon lambda 2 is equal to, what is lambda 1? Lambda 1 is H upon 2. M is mass of electron, and what we have done here, which formula to use? This one. Lambda is equal to H upon square root of 2m kinetic energy. This formula we will utilize. So lambda is equal to H upon square root of 2m. Now lambda 1 kinetic energy, first one, so it will be 50E. This will get here. Lambda 2, it will be H upon square root of 2 into mass of electron into second kinetic energy, and it is 200E, right? So this is the ratio. Again H cancels H, 2me cancels 2me, charge E cancels charge E, so it will be square root of 200 upon square root of 50. So which will be basically what? Square root of 200 by 50. So it is what? It is square root of 4, which comes out to be 2. So the answer is what? Lambda 1 by lambda 2 is basically 2:1. So this is the ratio of their wavelength, 2:1. So this is how we utilize these two formulas, or we can say all three formulas, in solving our problem. Now important thing is that de Broglie concept is applicable mostly to the microscopic objects, right, like electrons or protons, but not to the heavier objects or the objects which we can see easily through our eyes. How do we define this thing? See, understand this thing, that we will take two cases, case 1 and case 2. In case 1 I will take electron, and let's say the electron is having the mass of 9.1 into 10 raised to power minus 31 kg. This is the mass of electron, and let's say this electron has the velocity of, let's say, 2 into 10 raised to power 6 meter per second. This is the velocity of electron. Similarly in the case 2 I will do what? In case 1 we have taken the electron, which is a microscopic particle. In case 2, let's say we take the tennis ball. Now in the case of tennis ball, let's say its mass is 250 grams. So it will be how much? It will be 0.25 kg, because we have to take the mass in kg. And let's say its velocity is 30 meter per second. Its velocity is 30 meter per second. Now in both the cases I will try to calculate the lambda. So here in the case of electron, lambda will be h upon p, right? So what is h? H will be 6.626 into 10 raised to power minus 34 upon mass. P means what? P is momentum, which is mass into velocity. So I will take 9 approximately, so into 2 into 10 raised to power minus 31 into 10 raised to power 6. So this is the lambda of electron, right? Similarly in the case of tennis ball, let's say calculate here, it will be 6.6 into 10 raised to power minus 34 upon 0.25 is how much? 0.25 is basically 1 by 4, right, into 30. This is what we have obtained. Now lambda of electron will be how much? Here we have 9 into 2, so if we cancel it, it will come out to be 2 under 2, it is 3.3, and further solving it, let's say this is 3, it is 1.1, and upon doing it 0.3 into 10 raised to power, now we have minus 31 below, minus 34 above, so it will be minus 34 plus 31 minus 6, so it will be 0.3 into 10 raised to power how much? It will be 40 minus 34 minus 6, it will be minus 40 plus 31 minus 9, so it will be 0.3 nanometer, right? This is somewhat value we have obtained, which is measurable. Basically we measure the wavelength of electrons in the terms of angstroms, right, or picometer or nanometers. But when it comes to the ball, in that case if you calculate it, it will be how much? It will be 66 divided into 4 divided by 30 into 10 raised to power minus 34 meter. So you see the value, the range of value is in the terms of, in the powers of 10 raised to power minus 34, which is near what? Which is even below the Fermi meter. This lambda b is even below 10 raised to power minus 15 meter, right? So which is very difficult to measure. That is why if the particles are having very small size, or we can say they have very less mass, generally the microscopic particles, in that case the wavelength is possible to be measured. We can possibly measure the wavelength. But in the case of macroscopic particles like tennis ball, their mass is huge, their velocity is very less. In such cases it is very difficult to find the value of wavelength, because it is not coming under the radar of measurement, right? So this is the basic holistic approach about the de Broglie concept. So we have understood what we have just gone through the concept, and we have gone through the equation derivation also, how we have derived the equation, the 3 important formulas we have gone through, and along with the 3 important formulas we have solved 2 equations, 2 questions also. The first question was this one, second question was this one, and the next very important concept, that de Broglie concept is applicable mostly to microscopic objects. This we have proved here, right? This we have proven here. So I hope you understood the concept. I know this video was a bit lengthy, but you don't have to watch any other lecture, just go through it, and everything which is written in your book, NCERT or any kind of JEE Advanced, NEET or mains level book, you will find all the content here only, right? So stay tuned for the next lecture, because next lecture will be further from the more important topics of atomic structure. So thank you, have a good day, bye bye.